Nikola, Rajic, Customizable Parametric Frameworks for Bridge Design in Large-Scale Projects. Izvolite.
Okay, thank you for the introduction. As it says here, my name is Nikola Rajic, and I will be presenting the customizable parametric bridge design for large-scale projects. So, what is the purpose? Automation is the main thing that we want to do in today's engineering. So, in typical bridge design process, we have several steps. For example, we have the first step. We assume some kind of bridge layout. We have some loads detect on our structures. We have, for example, from cards, we read the peak acceleration for the seismic loads. We assume some kind of tendon layout, and we assume also reinforcement for our structural elements. And then in the next step, we do the load analysis. We calculate the magnitudes for the dead loads, for the superimposed dead loads. We also analyze traffic loads. We also analyze the seismic loads based on these input data. And in the third step, we generate our finite element model. So this is the main step in bridge design process. We generate our FE mesh. We apply our boundary loads. For example, we apply point spring supports on our piles. Maybe we have some construction phases. We have to deal with them as well in our FE model. And we apply those loads that we have previously analyzed in the second step. And after that, we perform design. And in the last step, we do ULS and SLS checks. And if they do not pass with our initial assumptions, we revert back to the first step. We maybe change something in the bridge layout. Maybe we modify our tendon layout or something else. And we go through these steps once again. So then we perform again the last step, the ULS and SLS checks, and they usually do not pass again. We do this cycle several times. So we repeat the second and the third step several times. So these steps need to be automated if we want to have automated bridge design process. So if we manage to do this, if we manage to automate the second and the third step, the only thing that we are dealing with is the first step. We conceptually look at the bridge. We deal with how our tendon layout should look like. Then someone else does second and third step for us, and we just do ULS and SLS checks for our super and substructure pass or not. If they do not pass, we just change the initial data, and these second and third steps are automated. Why is this great? If we do manually our model, we do repetitive tasks. Repetitive tasks are error-prone. If we do something that is boring, we manually do something. If that is repeated, then errors are most likely to happen. If this is automated, no errors can happen because automation does this instead of us. The second thing why this is great is because we have standardized modeling. If this is implemented in some company, then every bridge model is done the same. We do not have now situation that one engineer does something one way, he names groups of elements one way, he has his own load combinations, and the other engineer in the company names groups some else in the other way, or he has his own set of load combinations. So we do not have any more this confusion. Everything is standardized. And the third thing that I think that is the most important is that engineer is not anymore focused on technical details of using software. Now, if this is automated, I do not think should the upper node be master node and the bottom slave, or vice versa. I do not apply point spring support. Someone else does that for me. I look at that bridge from the conceptual way. I do high order things on that bridge. I think about that bridge as a concept and not as a technical detail of how should I type in this software and do the modeling. And the last step is that this thing doing this thing in automated way is extremely time efficient, because most time we spend manually modeling these bridges. So if we can save this time, that could be great. So what are these possibilities for this in today's software? In software that come out of the box, we usually have some wizards. And these wizards are good for most cases, but these cases usually do not, in practice, work. For most cases, they do not work. Why? Because, for example, using wizards, it does not create complete models. You know, if you look at these models that are created from wizards from one software, MASE, for example, we do not have, for example, foundations on these models. So these wizards generate models for us, but they are not complete. They are not ready to use. We need to modify them. We need to add something to them. And if something changes, we use that wizard once again. It generates once again model, but that it is not complete. We need to work on it manually to make it design ready, to make it for engineers just to click perform design and use it. The other thing, they are not customizable. If we have some specific project requirements, we cannot modify this code. This code is implemented inside the software, and we cannot open and look at it and modify its code. And it is also software dependent. We need to have that software in order to use this wizard to generate models for us. And what can we do? What is the possibility to make something that is customizable and that works, that can generate models for us, that we need zero manual work for them? For example, we can do something like this. In large scale projects, we can cluster bridges. We can say, for example, our company has a task to design 100 bridges. 1/3 of them are solid slab bridges. The second group is, for example, box bridges, and the third one is semi-prefabricated T-beams with in situ slab. So we think parametrically like this. We can generate 3 parametric models, or, for example, even better, we can create one single general parametric model that covers all of these cases. And then comes the next part when we have to generate the parametric script. That is code, for example, in Python. We code everything, and this is the step that requires some basic or intermediate programming language. And then this parametric script does the second and the third step from the previous slides for us. It generates our FEA model, and then we only import that data in our structural analysis software. And for example, the parametric framework that is presented in this work is based on this. It has parametric model that uses parametric script, and it communicates with software called MASE. Let's look at some simple example that I have also presented. It is available on YouTube. It is a webinar called Parametric Bridge Design with MASE NX. If someone is interested, please feel free to take a look at this webinar. In this webinar, I generated one parametric model that is box girder superstructure. And what are the parameters for this bridge? Parameters, we select parameters based on the group of bridge that has similar properties, but also it has something that is different. For example, in this parametric model, we can select number of spans. So we can analyze single span, 2 spans, 3 spans, for example, n spans of this bridge. We can add magnitude of STL loading. We can also select cross-section properties, and also we can add, for example, the radius of curvature. And using this parametric model, series of structural calculations were done, and you can see on the right that we have looked at the torsional reaction, because this bridge is in curved alignment. For vertical loads, it also exerts torsional moment as a reaction. So if you can take a look at the graph on the right, on the bottom right, you can see if the curvature is getting lower, if it is in a much sharper curve, then the torsional reaction gets much with much higher magnitude. So this is one simple example, so-called theoretical school example. But also, this thing is able to scale it up, to make one general parametric model that can cover a vast majority of bridges. And for example, in the company, DB Engineering, we have implemented this. And this is one parametric model that covers a lot of things. For example, if you can see this parametric model, it works with 4 types of superstructure. It covers solid slab superstructure, it covers box section, composite I section girders, and also T-section rib bridges. You can generate bridges with all of these superstructures. For example, you can generate also bridges that have a deep or shallow foundation. It can be in a straight alignment or also curved alignment. And for example, you can generate integral or semi-integral connections with piers and abutments. So it covers a lot of cases, and it is also customizable. It has been programmed in Python, and it is adaptable for each project that comes, for every new project. If for some new project, some of the engineers in the DB engineering has tasked to design bridge that has also expansion pier on one or the other side, or so on the both sides, then they send signal to me, can you please add possibilities for this parametric model to include this as well? And it takes a couple of days for me to develop this, and then engineers have possibility to model this bridge as well. So that is the customizable thing of this framework. It can adapt to every specific project. Also, important thing is that this parametric model does automatically load analysis. It applies all loads, generates all load combinations. It also adds automatically tendons, strands. It is possible to model also pre-tension and post-tension to these bridges. And also, it is possible to add automatically reinforcement to all elements. So what is the result of this parametric model? The result that comes out of this model is design-ready model. So engineers get one piece of data that they import inside MASE Civil, and they have zero work, zero manual work. All that they need to do is to press design, perform analysis. And analysis is done automatically by MASE Civil, and they just check ULS and SLS criteria. If they pass, everything is good. If they do not pass, they just modify parameters, maybe change cross-section dimensions, adapt new tendon layout, and then parametric model generates another input data. They import it inside MASE Civil, perform analysis once again, and check results. So there is zero requirements for manual work. And why is this very important? This is very important because engineers are no more FEA modelers. They do not focus on how to model this kind of bridge. Maybe some changes are required by road designers. Sometimes road designers change alignment from straight bridge to curved bridge. Remodeling that is extremely hard. You know, you need to translate nodes. You need to rotate some elements. So the model becomes a mess. But if you use this parametric model, it is just several clicks. You just change alignment from straight to curved, and new model comes out of it, and you just press perform analysis. This sounds maybe not real, but believe me, it is. Let's check some details. How is this program organized? This automation program is organized like this. It has one Excel-based central input files. So all engineers are familiar with Excel, so they use this Excel file. They go through all of these sheets, and they input data. For example, first sheet is main girder geometry, second sheet is construction phasing, etc., etc. They input all of this data inside of this central data. Then the parametric model generates all of the data. They need zero manual work. And what is the result? The results are, for example, load analysis reports So if they need to prepare a calculation report, they already have this load analysis sheets that they can use in their calculation report. Also, reports for tandem quantities are also present, etc., etc. So let's see this software in action. I will play this video. I don't know why it is not working. Enable it. Okay, so let's see this model in action. Engineers go through this Excel file. They input these parameters. They define geometry, soil condition, construction phases, rebar, tandem data, loading input data. They publish this input file for model generation. The model is generated. This is one textual file that they import inside MASE Civil, and everything is generated. As you can see on the left in this work tree, everything is done automatically. So zero work is needed. Let's see another example. This one shows customizable features of this software. For example, initially this software was able to model only straight bridges, and at some point we had a lot of bridges that were in curved alignment. So the request for me was to make this software possible to model also bridges that are in curved alignment. So this was done as well. As you can see here, alignment length, alignment radius is entered, and also all other data. Model is generated, and you can see here we have also bridge that is curved. So this is also a possibility of this software. And let's see the last one. In this last one, you can see also the workflow for this software. This is from the latest version of this software, where box girder and solid slab bridges are also introduced. So engineers, once again, they select now the main girder cross-section key, for example, 0, or T-section bridges, etc., etc. They input all of the other bridge parameters, publish model flow analysis. They get these load analysis reports, and also they get this output textual file that they import inside MASE Civil, and they get complete model that requires zero manual work. Everything that is needed is to press perform analysis and check ULS and SLS criteria. Okay, that's it. Thank you for your attention.
Thank you, Mr. Rajic, for such a nice presentation and presenting the capabilities of, as I understand, your software that you are developing or your company is developing.
Yes, I am the developer of the software, and DB Engineering is user of the software. Yes.
Okay. Thank you very much.
Thank you.
Со ова ги исцрпивме презентациите за оваа сесија. Ви благодарам на сите за присуството и како што е редот, ве покануваме на свечената вечера која што е закажана за 21 часот. Ви благодарам и се гледаме. Мислам дека нема такви. Excuse me, can I have your attention, please? One technical requirement. So anybody who has these headphones for translation, please leave them on the chairs. Thank you very much.